Hello, everyone, and thank you for being here virtually. My name is Yannick, and for the next 10 minutes, I'd like to talk to you about the identification of vibrations corresponding with heart sounds using vibrational cardiography. Here's the outline. We'll start with a quick background just to make sure we're all on the same page. We'll go over the strengths and limitations of different cardiography methods. This will give us a better understanding of what we're trying to measure. It'll also lead us into the analysis. We'll then go over the results, and hopefully this will bring up a few questions. So let's get started. We all know that cardiography is important. The activity of the heart tells us a lot about our health. So if we can build a biomedical device to monitor it, then we can solve a lot of health problems, sometimes even before they happen. To monitor cardiac activity in real time, let's look at our options. Here are some of the most common cardiography methods. Echocardiography produces high accuracy, content-rich information. It can detect cardiac events like ventricle and valve movement. We can use these cardiac events to measure cardiac time intervals. Unfortunately, echo is also expensive, it's not portable, and it needs a trained technician. So it's not very accessible. If we need high accuracy, we could also use electrocardiography. An important feature of the ECG signal is an R peak. It indicates when an action potential is sent to the heart to make the ventricles contract. The distance between two consecutive R peaks is the beat-to-beat duration. BTB is most commonly used in its inverse form, heart rate. The ECG RR time interval is actually a clinical standard for measuring heart rate, but it has a limitation. Since ECG measures the signal sent to the heart, it doesn't actually monitor the activity of the heart. We could monitor this activity electrically through its impedance. We know that the impedance of the chest changes during the cardiac cycle, so we can record that using impedance cardiography. An ICG waveform indicates the transitions between the systolic and diastolic phases in a cardiac cycle. Its limitation is that there isn't a good way to analyze ICG signals. In fact, ICG annotation schemes are known to be subjective. So let's look at mechanocardiography. When the heart pumps blood, it moves the whole body. That movement can be recorded with ballistocardiography, but it isn't portable. Although when the heart beats, it produces vibrations and sound too. Heart sounds are pretty easy to monitor, which makes phonocardiography very accessible. But the sounds don't contain much information, and it's highly susceptible to noise. So let's look at the vibrations instead. There are two methods that detect vibrations at the sternum. Seismocardiography detects linear accelerations, and gyrocardiography detects rotational gyrations. Of course, they're both coupled and orthogonal to each other. They even use the same sensor. And this combined method basically detects vibrational motion in 3D space. So we call it vibrational cardiography. VCG waveforms have strong oscillatory features that coincide with cardiac valve movements. These valve movements happen during cardiac phase transitions, that is, between the systolic and diastolic phases in the cardiac cycle. So to recap, cardiac phase transitions generate vibrational waves, which show up in a VCG waveform as high amplitude oscillations. So how do we identify these oscillations? The oscillatory features appear in two separate segments of the cardiac cycle. You can see them as green and yellow blocks highlighted in the diagram. Most identification algorithms focus on the first segment. That's because the vibrational pulse, V1 in VCG, happens at the same time as the S1 sound in PCG, the R peak in ECG, and the B point in ICG. So it's pretty easy to verify. It's been identified using algorithms like the hidden Markov method and the autocorrelated differential algorithm, among others. The ADA identifies high amplitude oscillations by amplifying variations in the signal. For this study, we upgraded the ADA to measure both the vibrational pulses V1 and V2. The second pulse happens around the same time, V2 happens around the same time as the S2 sound, in PCG, and the X point in ICG. So how do we extract vibrational pulses from the VCG signal? In other words, how do we increase their signal-to-noise ratio? Think of a perfect signal with an infinite SNR. The signal would be a series of delta functions, right? There's a peak for every time something happened, and otherwise it's just zero noise. But how realistic is that? I mean, in real life, there's always a little noise. So a mostly clean signal would look like a series of Laurentian peaks. And that's what we get from our algorithm. We converted the acceleration to jerk by differentiating it. And for gyration, we just squared the signal to get a measurement related to its rotational kinetic energy. And voila, Laurentian peaks. So for the next step, how do we know that these Laurentian peaks have actually identified a vibrational pulse? If we look at the three VCG axes, we can see that there's a peak in each axis. And these peaks happen at around the same time. This tells us that they're measuring the same thing, which, considering the nature of jerk and RKE, could only really be a vibrational pulse, or interpreted as so. So now that we know that we're detecting vibrational pulses, how do we know that these pulses are actually related to cardiac phase transitions? Well, one indication is the fact that the processed waveform only has two peaks in each cardiac cycle. But just to verify that hypothesis, we also recorded ICG and ECG. The experimental setup was connected using the color coding you see here. We had our VCG signal routed from an inertial measurement unit through a Raspberry Pi. The ECG and ICG were acquired using a biopack. The waveforms were synchronized with the pulse generated by the biopack. We tested 15 subjects between 18 and 39 years old who were in relatively good health. Now for the results. First, we compared the timestamp of V1 and the ICG B point with the ECG R peak. The correlation coefficients were 0.9987 for VCG and 0.9824 for ICG. Bear in mind that the ICG value was obtained after discarding data points that were more than 10 BPM away from ECG. The coefficient was still lower for ICG because of its annotation scheme. So naturally, when we compared VCG with ICG, it had a much lower correlation. This already alludes to the inaccuracies that could occur when verifying cardiac phase transitions. Still, ICG was our best bet. We then looked at the second vibrational pulse, V2. Now remember that this cardiac phase transition has mechanical causes, which can't be detected in ECG, but it has electrical consequences which show up in ICG. So we compared the timestamp of V2 with the ICG X point. To do that, we measured their distance from a common reference, the ECG R peak. This told us that our measurement was in the right ballpark, but the accuracy was pretty low. So what's going on? Another way to look at this is by measuring how well the LVET follows BTB. We know that the systolic phase lasts for about 40% of the cardiac cycle. So we measured the fraction of BTB taken up by LVET, that is LVETF, and that gave us some insight. There were quite a few points above the correlation, which meant that our problem happened when the LVET from VCG was high and from ICG was low. Why would that happen? Well, we dug into the individual recordings. Apparently, the ICG measurements sometimes flatline. So we're currently looking into better ICG annotation schemes. If you have any suggestions, please let us know. Otherwise, we might need to switch from ICG to some other detection method. At least, we need to find a better scheme to know which points weren't identified properly and which were. So just to summarize, we recorded simultaneous VCG, ICG, and ECG. We processed the VCG signals to produce Laurentian peaks that indicated vibrational pulses. There were two peaks in each cardiac cycle. We compared the first one with the ECG R peak and the ICG B point. The second one was compared with the ICG X point using two approaches. We compared its distance from the ECG R peak and also the LVET as a fraction of BTB. The results looked promising. Our next step is to improve our identification algorithm and also our verification scheme with ICGs so that we can improve these results further. And with that, I'd like to thank you for listening. If this topic piques your curiosity, we also have 3 other talks this week that you might be interested in checking out. Also, if you have any suggestions, questions, or doubts about the study, I'd be happy to hear from you. Thank you.